so in this lecture, we'll actually show that the L1 minimization recovers sparse vectors. Okay, so the goal is same thing as before. So we have X in our N. X is as sparse. And we observe Y equals A X. And we try to recover X. I don't really think of A as a short path, so A is M by N. Right, with M a lot smaller than N. Right, so that the system is an indeterminate system, and we try to recover X, estimate X via this optimization problem, find the minimum of a norm such that AC equals 1. And now the goal, so the goal of today, and actually of next one too, right? So the goal is to show or understand when, show that, right, for many cases, I should say, right, it all depends on A in many cases. The solution is X, right? So that when we solve this, we actually do recover the sparse vector. Okay, now the question is how are we going to do this? So there's a few different ways of doing it. One actually goes to the restricted isometry property, but let me try to sort of motivate one possibility of how one would try to show this, right? And actually I'll explain more than one way, because as we go into other problems, like if you want to work out the matrix completion or things related to lining convolution, centrifugal, many other problems, different super resolution, and so on. Different of these approaches work better in other settings, and so it's a good idea to review a few, at least to briefly describe them. Okay, so let's say that, let's go by contradiction. Okay, so by contradiction. Okay, let's say that there exists another Z different than X, such that it is actually optimal to this, right? So that we have that Z is, say, at least as good. Right, because at the end we want to show that the unique solution, right? And of course that it's still feasible, right? Okay. So this means, right, in particular, Z minus X needs to live in the null space. Right, so let's take V. Let's define V to be Z minus X. Now let's say that S is the support of X. Right? And let's assume that the support is exactly of size S. If it's not of size S, just pick a set S that contains the support and is of size S. So most generality, because if we get something that includes the support, everything still works. So let me just assume that the support is equal to S. Okay, so let's see what we know about this vector, V. Okay. So first of all, V is in the kernel of vector. Right? V is 0. Right? In other words, V belongs to the kernel. Okay, so if we show that such vector V cannot belong in the kernel, then this can't happen, right? So you're already seeing here Gordon skips through a mesh popping up. See, well, let's work on this a little more. Right? What else do we have? We have that, Z is equal to X plus V. So X plus V, one norm, needs to be smaller or equal than X, one norm. And now let's look at this expression, right? So in the support of X, right, X is only non-zero in the support of X. So if V has any values outside of the support of X, you can only be making this norm bigger there, right? Because there X is 0. So somehow you see making the norm smaller in the support enough to compensate for how it can make potentially the norm bigger outside of the support. Right? So let's try to make this a little more precise. Right? So if this happens, then let's split this norm. Right? This is the same as, maybe I'll carry out. Right? So this now, let me do it the other way so that I can carry out expressions. this is what? This is the one norm in X, right? The L1 norm has this property that the L1 norm is the sum of the L1 norms of each part of the support, right? Because it's just the sum of them, so those of the increase. Right? And so this I'm going to take to be the vector only on the entries, only on the coefficients in S, right? Plus the ones outside of S. Right? This is what this is. But now, well, here, right, XS plus VS, sure. But X outside of the support is 0. So this is just L1 norm. Okay. Now let's look at this, right? So this is for sure positive, but somehow the fact that this will have to be a lot smaller than this. Right, but now we can see by exactly at most how much smaller it is by just the triangle inequality. Right, so we can just do triangle inequality. For sure, this part is not smaller than this. Right, you have the L1 norm of XS. The most V can take out of X is its L1 norm for sure, plus. But now this is exactly, X is supporting S, so it's exactly the L1 norm of X. So let's look at this. So what does this mean? This means that we must have, right? We must have that this V, right? If this is going to be smaller than that, it must be that this term is bigger than this term. So it must be that Vs, one norm, is bigger or equal than Vs complement. Okay, so it must be that this vector V needs to be in the kernel of A, and it needs to be very concentrated in this sense. Right? It needs to be very concentrated in this sense that so V, so that you couldn't see, I'm not sure if you could see this line, so I'll repeat it. Right? So all I did here was replace the L1 norm of XS by the L1 norm of X. Of course, they are the same because S is the support. But what we learned here is that this vector V, it must be that it has bigger L1 norms in this S entries than in the rest. Right? So this is a very special vector, right? Because it's a vector that is very, very concentrated in L1 norm in very few entries, in only S entries. And so now from this observation, we can take a few different directions. One possible direction is say, okay, let's fix X, and let's say, will it be that there is such a vector V that satisfies, say, this inequality here, for example, or this one, in the kernel of A. Right? And now we just have to measure the Gaussian width of this set for a specific vector X. And this is done in a few places. This gives there's many papers in the literature, I'll put some references in the notes, but this gives exact constants of exactly how we know that M will be something like S log n over S, log n over M, or log n over S, and we'll get this way we can get exactly like the exact constants and get very, very, very good predictive behavior of the asymptotics of this. And this is done sometimes through, by measuring Gaussian width of descent cones, which is basically this, right? When is it that the L1 norm actually descends? And by something called integral geometry, so I'll put the references in the notes. But another approach one can take, right? So that's the approach that gives sort of the exact constants for a specific X. But one approach that we can take is we can say, well, if there isn't any vector V in the kernel that is this concentrated in any set of size S, size little s, any set big S, right? If there's no concentrated vector in the kernel, then it must be that for any sparse vector X, I can always do recovery. Right? So we're doing a uniform statement over all sparse vectors. Okay, so in particular, what we have to understand is the Gaussian width of this set. Right? So let me give this name. Say the set of very concentrated vectors. Okay. So this will be V, in say Rn, or I should put it in the sphere, right? Because we're like measuring Gaussian widths in the sphere, such that there exists a set S, subset N, with size S. This is very well concentrated here. Okay, so now I define the set of concentrated vectors in S coordinates. And basically what we see here is if, right, immediately what we saw is if X is not optimal, or not the unique optimum, then there must exist V in this set. Right, I'm indexing this by little s set. Such that AV equals 0. So of course we can now take the converse of this theorem, right? The counterpositive of this theorem, and we can just say that, that now if there isn't any vector V in the kernel satisfying this, then X always needs to be optimal. Okay, and so this motivates the following definition. We say, give me the definition. We say A satisfies the S null space property. So S says null space property if this is an intersect with S. Right? If CS intersected with the kernel of A. Okay, and so then we immediately get a theorem. Theorem if A satisfies the S null space property, then X is the unique optimum. Of L1 minimization, right? And so provided that A satisfies this null space property, then we know immediately that we can recover the sparse vector by this L1 optimization. So now what we have to try to understand is when is it that A satisfies the null space property? Right, and then I'll also describe this briefly, another way of trying to get at this via duality. So how do we show something like this? Well, okay, let me first say, before showing this, that there's another theorem one can show that I will not show because I don't think the proof is as enlightening as the one I'll show you now. But actually, A satisfying the 2S 1/3 RIP implies that A satisfies the null space property. Okay, that's the reference. There's a reference to the right, of course, we need an RIP for 2S vectors, right? We've already seen that. And once we have an RIP for 2S vectors, then this implies a null space property. Okay, so now our goal is to understand how large does N need to be for a random Gaussian matrix to satisfy the null space property. Right, so now we are simply in the realm of Gordon's theorem, right? Now we can just use Gordon's theorem. All we need is that CS doesn't intersect the supported A, right? So we can take A to have random Gaussian entries, so IID Gaussian entries. And here, because we don't even care about the scale, we don't care about even keeping the norm, right? We just care about not sending to 0. We don't even need to worry about normalizing. Right? Then we know via Gordon, right? And say Gordon's theorem or Gordon escapes through a mesh, right? I mean, they all will imply this. Then if M is much bigger, right? Up to some constants, I'm not worrying so much about constants. and the Gaussian width square of this set, then A will satisfy the S small space property with high probability. Okay. And so now the question that we need to ask ourselves for the rest of today is, what is the Gaussian width of this set CS? This is really what we need to compute. Right, so for sure it's bigger than of S sparse vectors, right? Because the S sparse vectors in particular, they satisfy this inequality, right? Just take the support. Then this will be and 0, this part will be 0, but there are potentially many other vectors that satisfy this. And so this is what we need to understand. And so once we compute the Gaussian width of this, Gordon's theorem immediately tells us that this can never intersect anything in the support. This is high probability if I take a Gaussian. So immediately get a theorem of the type, if I draw a Gaussian, then this whole procedure is going to work. That if I measure this sparse vector, I can recover it with L1 optimization.